All right, let's dive right into this comprehensive visual study guide. We've designed this explainer to completely demystify the architecture and reactivity of aldehydes, ketones, and carboxylic acids. Whether you're a chemistry student gearing up for a brutal exam or just a focused learner who's fascinated by molecular engineering, consider this your ultimate roadmap. We've actually grouped all this content by difficulty, so we're going to start with foundational basics and build all the way up to advanced reaction mechanisms. It's basically a perfectly structured test review.
Here's our roadmap for today. 1. Anatomy of the carbonyl core. 2. Naming and physical traits. 3. Synthesis web. 4. Core mechanisms. 5. Diagnostic lab tests. And finally, 6. Real-world impact. Let's get into it.
Section 1. Anatomy of the carbonyl core.
To truly understand chemical reactivity, we've got to start right at the foundation. Imagine looking at this molecule from an angled side view, while a top-down perspective shows perfectly flat 120-degree trigonal planar geometry. That angled view reveals something absolutely crucial: extreme polarity. This polarity creates a highly electrophilic or electron-loving carbon center, marked with a partial positive charge, and a nucleophilic oxygen center with a partial negative charge. This extreme polarity is literally the engine for everything that follows. Now, a really common exam pitfall is mixing up this charge distribution, so make a simple mental sketch of this bond geometry and lock it in.
Section 2. Naming and physical traits.
So, this molecular anatomy dictates exactly how we classify these compounds. The crucial thing here is comparing the structural differences. The defining trait of an aldehyde is that its carbonyl group occurs at the absolute end of the carbon chain, so it always possesses that terminal, easily reducible hydrogen atom. A ketone, on the other hand, is squarely embedded within the carbon chain. It's flanked by alkyl groups that provide structural stability and steric hindrance. Here's a pro tip. When you're writing your notes, try color-coding that terminal hydrogen in blue. It is hands down the fastest way to spot an aldehyde.
We turn those structures into a universal language using IUPAC naming, which systematically replaces alkane suffixes for rapid recall. You just tag al onto a 4-carbon chain to get 3-methylbutanol, or 1 onto a 5-carbon chain to get pentan 2,1. Just remember that numbering strictly begins at the carbonyl carbon. Now, common names often come from household biology. For example, formica means ant, which is the historical source for formic acid. Acetum means everyday vinegar, giving us acetic acid. A really quick memory mnemonic for these common prefixes is first apes play bongos, formic, acetic, propionic, butyric. Connecting these complex molecules to everyday household analogies just makes them so much easier to remember, right? Think of this physical spectrum as your cheat code for rapid exam recall, proving that boiling points scale aggressively upward based on intermolecular forces. At the bottom rung, hydrocarbons rely on weak dispersion forces. Aldehydes and ketones sit a bit higher, at around 325 Kelvin, thanks to the dipole-dipole interactions of their polar core. But the absolute heavyweight champions, the carboxylic acids. They engage in intense dimer hydrogen bonding. They're literally linking 2 molecules together in a tight ring, and that pushes their boiling points way over 390 Kelvin.
Section 3. Synthesis. Forging carbonyl compounds.
Okay, here is your ultimate synthesis flowchart. The oxidation state of the carbon atom strictly determines the molecular class. Notice how chemists literally navigate up and down this carbon continuum. By utilizing specific catalytic reagents, you can carefully oxidize alcohols into aldehydes and ketones and push them all the way to carboxylic acids. Or you can forcefully reduce them all the way back down to alcohols or even basic hydrocarbons using reagents like lithium aluminum hydride. It's a really elegant, completely reversible web.
Let's look at some specific tactics. A controlled oxidation of a primary alcohol easily yields an aldehyde. But what if you want to structurally lengthen the skeleton and build a carboxylic acid? Well, you can't just oxidize, you need to actually build. To do this, you deploy Grignard reagents alongside solid dry ice, which is just carbon dioxide, to elegantly insert a brand new carbon atom into the chain. Ascending the chain by 1 carbon is an absolutely critical maneuver to memorize for any advanced synthesis problem you're going to face.
Section 4. Mechanisms and chemical reactivity.
The core mechanism of nucleophilic addition is incredibly highly tested, and this 3-step progression perfectly highlights the dynamic structural shift taking place. Because that carbonyl carbon is coplanar and flat, nucleophiles are forced to attack directly from a perpendicular angle. As the attack lands, the molecule visually pops up, rehybridizing from a flat 2D planar molecule into a 3D tetrahedral alkoxide intermediate. Finally, it captures a proton to form a neutral addition product. Visualizing that 2D to 3D popping motion is the key to mastering this mechanism. I'd highly recommend color-coding your nucleophile in red and the carbon center in blue in your notes to truly lock down this pathway. Now, the alpha hydrogen effect splits reactivity into two completely different worlds. And listen, an enormous pitfall for students is simply forgetting to check for adjacent hydrogens. If a molecule has adjacent alpha hydrogens, like acetaldehyde, the electron-withdrawing core makes those hydrogens highly acidic, leading straight to aldol condensation, where molecules link together. But if it lacks alpha hydrogens entirely, like formaldehyde, it is forced into the Cannizzaro reaction. In this disproportionation event, one molecule gets oxidized to a salt, while its partner gets reduced to an alcohol.
For carboxylic acids, reactivity is simply a matter of anatomical precision. Breaking the OH bond unleashes its high acidity, evolving carbon dioxide gas when reacted with weak bases. Just like the classic baking soda and vinegar volcano from grade school. However, if you cleave the COH bond on the other side of the group, you open up entirely different pathways to fuse molecules together, such as heating with alcohols to yield an ester, or using dehydrating agents to fuse two acids into an anhydride.
Section 5. Diagnostic oxidation tests.
In a practical laboratory setting, or when you're staring down a complex exam scenario, you need to know how to rapidly differentiate between an aldehyde and a ketone. Think of this review as your rapid visual recall sheet. Because aldehydes possess that extractable terminal hydrogen we discussed earlier, they easily succumb to mild reagents. Adding Tollens reagent creates a stunning visual confirmation. A literal silver mirror coats the glass test tube. Fehling's reagent triggers a red-brown precipitate. Ketones, on the other hand, lack that terminal hydrogen and completely resist these oxidations, providing a clean negative result. Also, definitely keep the Iodoform test in your back pocket. It specifically flags methyl ketones by yielding a bright yellow precipitate.
Section 6. Real-world utility and impact.
The exact same carbon-oxygen double bond that drives our textbook mechanisms is actually the foundation of modern industry. On the biological side, the aromatic aldehyde of vanilla gives us incredibly complex foundational flavors and scents. Industrially, acetone and hexandioic acid act as the critical precursors for producing nylon 6,6, a super durable synthetic polymer used in textiles worldwide. Meanwhile, derivatives like sodium benzoate act as widespread food preservatives. The carbonyl group truly is an engine driving both biology and real-world manufacturing.
So, before I let you go, let's do a rapid-fire review with 3 practice questions. 1. What geometry does the carbonyl core have? 2. What reagent creates a silver mirror? And 3. What reaction happens if a carbonyl lacks alpha hydrogens? Lock those answers in. As you use this study guide to master the mechanics, ask yourself, how might understanding this incredible chemical engine empower you to create the life-changing materials of tomorrow? Keep reviewing those molecular structures, and I'll catch you on the next explainer.